Okay, let me see. I go to the right. So we're going to discuss two more current mirrors today, and then before we move on to the next chapter. So guys, can you guys get quieter? Yeah, thank you. So for this one, it's called a Wilson bipolar current mirror. Remember when we talk about the BJT-based current mirror, we have an issue with the base having current flowing through it. So that's going to like alter the current between the two matched transistors because there's current in the base. So the reference current doesn't always represent the current actually in the other one that needs the current source. So Wilson designed this current mirror to alter the behavior of the BJT-based current mirror so that it has less dependency on the beta, because beta is 100, it's not infinity. If a beta goes 1,000 or a few thousand, then we wouldn't have to worry. Like MOSFET, there's no current in the gate, so we don't have to worry about it. But this one always have current flow. So what he did was, instead of having one current mirror, it just looked like something like what we did before, like the cascode, similar to that, but it's not a cascode. So what he did was, instead of having these two like matched transistors to form a current mirror, and he added another transistor on top of there, like Q3. By adding Q3, and eventually you'll find that the current IC or current IO flowing. So the dotted line, it shows where we're going to connect the actual amplifier. So what we are concerned is IO. What we want is IO as close as possible to iReference, because iReference is something that we design, and IO is the result. So we want to use IO, but we want to know what IO is. IO is not something you can measure or you can see, because that's a result of this whole current mirror. But we always know how much reference that we design for. So therefore, by doing this, you'll find out that IO is relatively closer to iReference if you compare to the just regular like one current mirror. And analysis on this one is very simple. It's just based on the current relations between the different circuit. So if we want to duplicate that analysis process, and then we can figure out what's the relations. Like from the bottom, it's already showing on the left hand, but we just want to rewrite it so that you understand how this. So on the left hand, we have this one, and then on the right hand, we have another transistor, and then we do have the base connected to the collector of Q1. So Q1 is the main player, and Q2 is the companion. So we know that there's always a current flowing in each of this base of this transistor. So this current here, this current here. So what we start with, we're looking at IC over here. Because the reason we look at IC, because you see this IC, nothing is connected to IC, so IC flowing here. So at the bottom, you will have IE, which is IC plus IB. And this is IB, so we know that how much IB is. IB is always 1 over IC over beta. So we get 1 over beta is IB. So IC over beta. And similarly, on this side, you also have IC over beta. And here, you have IC because these two transistors are matched. The transistors matched, so therefore this IC is the same as the IC over here. Now, there's current going this way, current going this way. So the current coming this way will be IC plus this two currents, right? Because these two currents coming this way, so we got this 2IC over beta, and this IC. So therefore, the current over here is going to be IC plus 2IC over beta, or it's equal to IC over times 1 plus 2 over beta. So that's the current over on the right hand, the total current. Now this current actually comes from, if you look at this one here, you have another transistor coming this way, and this is actually connected to the collector of the other transistor, which means this IC plus all this is the IE through this one. And then we will know how much current flowing at the base, right? You know the current IE, the total of these two is equal to IC. So therefore, we can find out that this current over here is going to be IE, what if we call this, so it's going to be this current over here, plus, divided by, so it's going to be IC 1 plus beta over 2, and then divided by beta plus 1. That gives you the current of the base current. So now you see on the right hand, on the left hand, you have this branch is IC, then you have this branch current that we found it over here. So the total current, you add this two, you get I reference, right? So let me give this a symbol. So this is going to be IB3. So this is the Q3. So this current over here is called I reference. So I reference is equal to IC plus IB3. And then so we can find I reference is going to be IC plus this one, so which is IC 1 plus beta over 2 plus 1 plus beta. So this is I reference. Now the current over at the here is IO. At the top, Q3 is IO that what we need. We know the emitter current. So we use emitter current divided by beta plus 1 times pi. We got that. So this one is going to be beta times IC 1 plus 2 over beta divided by 1 plus beta. That gives you IO. So now you can, since now you got I reference, you got IO, we can compare the ratio between these two. So that's what really the whole book is, I mean, the whole section is telling you is the reference between IO and I reference, and it becomes a very, the number very close to 1. Basically, you just simply put this one and the other one together, and then see here, I give you the numbers over here, right? So, which means by doing this design, you can have a reference current very similar to the current you want. But without doing this, we previously know that it's like 1% difference, because beta is 100, it's about 2% actually difference, because this one each base connected IC over beta. But this one will give you much better result. And then the next, yeah. So once you find the current relations, the other thing is that, okay, well, we know the current source that we discussed so far. For small signal, the DC current source actually becomes open circuit, but what's left is its output resistance. And then that resistance is pretty high. It's usually RO of MOSFET or BJT. So we use that like as a load to amplify to increase the gain and things like that. So how does this look like when you get into the small signal, what's left, right? Because the whole part over here, I mean, if you look at the whole part, is really just like a current source. Okay, so basically, for example, if in the future you say I have an amplifier and I want to use this current source to do, so this current source is the whole thing over here, and up there is your amplifier. Well, this becomes like a common, it could be could be common emitter, common collector, whatever that you want to call it. So, and we need to know what this is equivalent to. If this is equivalent to just an open circuit, the whole thing would break up. So therefore, there will be some sort of output resistance that we need to find out. So in order to find out the output resistance, we need to draw the small signal circuit. So the small signal equivalent circuit, you have 3 transistors. So we need to draw all 3 of them. The first one is Q2 over here. So we draw Q2 becomes RO2 GM2 times V pi 2. V pi is here. See, V pi is between base and emitter. So we have this one. Okay, now V pi 1 and V pi 2 are the same. I mean, that's how we got this current source. And then this transistor over here, we have V pi 2, we have R pi and RO, R pi 2 over here. And because the collector is connected to the base, so therefore the voltage VBS, you see, the same as the current source. So therefore we basically transfer this into 1 over GM. Otherwise, this will be like a V pi times GS. V pi times GM gives you the current. So this is equivalent to resistance. And R pi 1 and R pi 2 now becomes parallel because these bases are connected. So we have this. And across here is V pi 2, and it was same as V pi 1. So you got completed on the bottom. And the top Q3, you simply draw the circuit R pi 3 and GM times V pi 3 times RO3, and then the base of Q3, the base of Q3 is connected to the collector of Q2. Therefore, you have connected the base to this. Now you got the top circuit. If we want to get output resistance, what you do is you apply voltage over here at kind of the output, and then you calculate the current, and you use voltage divided by current, you get the whole equivalent resistance. Apparently, this circuit becomes a little bit tricky because it's quite complex. We have to do some manipulation or mathematics or node analysis. So, but the good thing that you see here, the whole thing here is one node, so it becomes a little easier, right? But the only thing you have to be careful is V pi 3 is across this resistor, which is the difference between this node and this node. So when you do that, you have to calculate the voltage across here, so that this voltage over here minus this voltage here gives you V pi 3, and you find GM times V pi 3, and you find that current, and then plus Vx minus the voltage over here gives you the current over here. So these two currents added together gives you the total current. Now you have Vx over Ix. So now you can find the output resistance. So it's not that simple, but it's fairly straightforward, which means you should be able to observe how to get it. So we're gonna neglect the actual step to derive the resistance because it's gonna take a lot of time here. So you guys can read it. And then we also let us say, oh, if I can do that for BJT, I should be able to do that for MOSFET as well. It's very so anything happens to a BJT, you can basically copy that to a MOSFET. So copy that to the MOSFET apparently becomes this. Now you might say, okay, well, there's no current at the gate, so it doesn't really help. That is true because MOSFET does not conduct current in the gate. So therefore, regardless of what you do, I/O is always same as I reference. I mean, strictly speaking, it's not 100% because there's early voltage things like that. But for the purpose of this class, we always consider them to be the same. So what's the advantage? Well, the advantage is that you get a bigger output resistance. How do you get the output resistance? Again, draw the small signal equivalent circuit, and then apply voltage over here and get the current, and use voltage divide current, you get output resistance. So the advantage of Wilson current mirror is to get the really output more resistance. Now, so this is a small signal equivalent circuit that you can draw, and you have 3 transistors. You have Q2, Q1, and Q3. So for Q2 and Q1, you see their gate is connected. And also the gate of Q2 is connected to drain of Q1. So if we draw Q1, start to draw Q1, and you find that the drain is connected, when the drain is connected, we'll always convert that current source into a resistance, 1 over GM. So a lot of students ask many times, why do you convert it? Sometimes, well, if the drain is connected, because the VGS is the same as VGS times GM current, so that's why you can convert it. So, and then RO1 is in parallel, and so that's VGS2. And VGS2, this gate is connected to Q2 as well. So on Q2, you have this circuit, but GM2 times VGS2 gives you a current over here. Now, we cannot convert this one into 1 over GM2 because the voltage over here is not the same as VGS2. VGS2 actually is here, okay? So that's why we can convert this one because VGS1 is the same as the voltage over here, but this one not. So we have this circuit over here, and on the top one you have GM VGS3 times RO3, and then you have VGS3 between the gate and the source. See, this is VGS3. One of the mistakes a student make quite often is simply taking the voltage of G3 as VGS, which is not correct. VGS is always the difference between gate and source. You always, unless the source is grounded, otherwise VG is not the same as VGS. Clear? So VGS is not the same as VG because VGS is VG minus VS, but VG sometimes is VG to ground. So in this case, for example, not to ground, but actually to here. So VGS is not VGS. VGS is this voltage minus this voltage. That gives you VGS. So anyway, you can manipulate this one again, probably take you half a page or maybe even a page to derive the actual resistance, but you can do it. I mean, it's mathematics. It's not purpose of our class today. So later on, Wilson also, somebody else said, well, if you do that, look like it's not balanced, maybe we should have the circuit really balanced so we can have a really good IC design. So they added on the Q4. It doesn't change much. Basically, it only changes the output resistance. Because this is on the reference side, and this is a load side, so adding this one doesn't do anything for all analysis up to this point. But until like you get really advanced stuff, say, oh, actually, the transistor, even though they are matched, because there's some gate is connected, some gate is not connected, actually there's a minor difference in there. When we get to the really high-speed computing, really like millions of transistors on a single like a 1-inch wafer, and you will say, oh no, that's not true. So that's why they try to do this, to do the balance. You can do the analysis on this one as well. See, if you do the small signal equivalent circuit, you find that there's another one here. So there's another circuit up to this point, but you can still do it. So that's a Wilson current mirror. Now, this is the last one. We call it Widler current source. The Widler current source, if you look at this, you will notice already, this is just what we learned before, a current source, but somehow there's RE over here. So that's the difference. If we remove this RE, this is exactly the BJT-based current mirror we had before. Why would you add this RE here? Well, the reason was, if we want IO, same as I reference, for milliamps, for example, the current, the resistance is in the kiloohms. Right? So let's do some math. So we want, if you have 1 volt, you have 1 milliamp, and that gives you 1 kilo ohm resistor. Basically, that's what you do. If you 10 volts, you have 1 milliamp, you have 10 kilo ohms. So that's why we see, you see the book is 1.5 volts, 1.8 volts, or 5 volts, and then you have 1 kilo ohm, 10 kilo ohms. It's always this number, not too big, not too small, because we always use milliamps and kilo ohms. But by maybe chapter 12, I think when I talk about the losses in amplifiers, you'll find that in modern design, milliamps is no longer the norm. Milliamps is too big, too big. like for you to design isolated, like a discrete circuit, 1 milliamp, who cares? It's so small. But when you put 1 million together, if each one is 1 million, 1 milliamps, how much current do you have? You guys do a quick math? Huh? 1,000, yeah. 1,000 amps. That's a lot of current. A lot of current. That's 1 million. That's like one chip. This big, 1,000 amps. That's huge. How can you get a 1,000 current into this small silicon? No, it's no way you can do that. This is not possible. You're right. So people are doing this MOSFET designing today. No more milliamps, microamps. They do microamps. Yeah, I square R losses. Yeah, but here we have not got to that point yet. Well, here's yeah, that's part of the reason too. But so okay, so go to microamp. Now, if you have microamps, you have 1 million transistor. How much amp current you have? 1 amp. Okay, fine. 1 amp. Good. We get that done. But so the problem is that if you get 1 amp of current, I mean, if you get 1 volt power supply, but we don't use millivolts power supply, by the way. We always use volts. But this is the beauty, I guess, of electrical engineering is that we rarely get down to like a millivolts. We always use voltage supply with volts, 1 volt, 0.5 volt, 5 volts, for this transistors. So now you have 1 volt again. You have 1 microamp. Okay, tell me how much resistance you're gonna need. 1 mega ohm. And then people find, okay, you solve one problem, but you create another problem. How do I create a 1 mega ohm resistance on a silicon? It's impossible. I mean, well, it's not impossible, but if you want to do it on a very small scale, it's not possible. So people saying, well, that's what the smart guys are doing in history. Riddler said, I can actually give you a microamp current, a current source at microamps, but I only need a kilo ohm resistance. How would you do that? Well, this is the smart part, how he did it. We're gonna go through probably just example so that's a little easier to understand. Okay, so this example you're probably familiar, right? This is a traditional current source without resistance at the emitter. How do you calculate the resistance? If we want I/O to be 10 microamps, which is 25, see, we can calculate, if we assume this both are in linear region, we'll know that from base to ground is 0.7 volts, but the collector is connected to base, therefore here is 0.7 volts. Okay, so we got 0.7. So and then the current, I reference, how do you calculate I reference? It's going to be like your VCC minus 0.7 divided by R1. And I reference is 10 microamps. Okay, so we get R1 equal to VCC is 3 minus 0.7 divided by 10 microamps. That gives you 2.7 or 2.3 volts divided by 10, so 0.23. So 0.23. So this gives you 0.23 or 230 kilo ohms. Well, it's not mega ohms, but it's still quite big. It's 230 kilo ohm resistance, quite big. So how do you reduce the resistance? Well, this is what happens. If we add a resistance here, this current mirror is altered that the VBE are no longer the same. Do you think the VBE is still the same? The B of Q1 is grounded, but the B of Q2 is not grounded. If you have current flowing, there's voltage drop. So there's voltage here. So this is not 0. This is maybe 0.2, 0.3. So if this one is working in the linear region, this is 0.7, this is 0.7. But if this is 0.7, but this voltage here, so the voltage over here is not 0.7. So if this is not 0.7, how much current would you have then? If the voltage reduces, the current reduces. Do you still remember how we calculate current, you guys? That's from chapter 5 or chapter 6. You remember IC is equal to IS times something? E to the VB minus, divided by VT. So that's why I give you VT from the precise VT is 25 millivolts, which means if VB is smaller, your IC is going to be smaller. Your IC is going to be smaller. So if the previous VB is 0.7 is 1 milliamps, it says here, this is important. 0.7 milliamp is 1 milliamps. So we need to find out what is VB or what is the current if VB is less than 0.7. So basically you can say, you can use this equation saying, I think also give you VP. Yeah. So you can say IC, IC is 1 milliamps. So we can use 1 milliamps equal to IS e to the power 0.7 divided by 25 milli. So if you do that, you can find IS, right? Because this 1 milli is given, 0.7 given, 25 given, you can find IS just by taking log on both sides. Divide by IS and take log this, something like that. Well, actually not. You basically do this. E to the power, you can use a calculator. I cannot get the answer. But then, so we got that. So which means if we, so 0.7 means this one here, because this one is directly grounded. So basically this has to be 0.7. So we got this one to be 0.7, and this is 1 milliamps. So this is 1 milliamps. So we now can find R2. So R2 will be, this is wrong, this is R2. So R2 is going to be 3 volts minus 0.7 divided by 1 milliamp. That gives you 2.3 kilo ohms. Okay, guys, because this is the typo. This is R2, not R1. So I found R2. So next step is I need to find IO. To find IO, let me see if I have one more space to write. No, okay, no, actually I don't have. So, to find R3, we need to find out what VB is, so that we can find the current. Or if we know current, we can find the VB, and then we can find the voltage over here, and we use this voltage divided by the current, we get the resistance. Now, IO is already given. It says IO, we want 10 microamps. So IO is given, which means IO is given. I can go back to this equation here. So I have this second equation is IO is 10 microamps now equal to IS times e to the power VBE over VT. Okay. So now this IS was solved from this circuit over here. So from here, you already got IS. So now simply plugging IS over here, you see, you only have VBE as an unknown. You can find a VBE just by taking, divide by IS on both sides, and then take a logarithm, and then multiply VT by the other side. You got it. So you got this one, you got VBE. Now you got VBE. Basically, this is VBE2. I say, so VBE2. So now you have VBE2. So you can easily find R3 is equal to VBE2 divided by IO. So this one we found out was, by the answer was 11.5 kilo ohms. Okay, so 2.3, the other one 11.5. We add this together, it's like 13.8. But the previous one example, to remember how much we got? 243. Or 200 something. Let's see what is 240, 230 ohms, something like that. Okay. So that's how you would find this Widler current mirror is very useful when you want to reduce the resistance and have to realize a small current. So it's interesting to know that the history of semiconductor devices, it's like BJT was forced. And it was there like in the 1940s, 1930s, and until 1960s, and people invented MOSFETs. But in the beginning, MOSFET didn't work very well. It was not stable, and a lot of people believe that MOSFETs will never like become mainstream. But fortunately, through many years of hard work, they found MOSFET was so good that it's even much better than BJTs from many perspectives. No base current, right? So that's a huge advantage. And then they can have this so small voltage drop across this drain and source, like the overdrive voltage only 0.2, VTA is 0.2, 0.5, but BJT has 0.7. So you need much less voltage to drive. And then current-wise, much smaller. So nowadays, in transistors, in highly integrated circuits, very large integrated circuits, BJT is less and less used. Mostly I use CMOS or MOSFETs. CMOS, later on we'll talk a little bit. It's just two MOS, PMOS, and NMOS together to form a CMOS, complementary MOS, okay, it's called. Okay, so maybe I just quickly show example. It find I/O in terms of iReference and the device WOL. So the current mirror often refers to matched devices, but sometimes we might need different amounts of current. So in that case, we simply change how much W to L ratio we'll have in each transistor. Therefore, we'll have different current. In this example, for example, if Q1, Q2, Q3, and Q4, therefore they're all matched, you would automatically get a current I over here, same as iReference. But if they're not matched, you would simply just write down, say, I2 equal to iReference times WOL 2 over WOL 1. If they have different width to length ratio, you get different amount of current. So Q2 can be this. But if you look at the Q2 and Q3, they're connected in series, right? So that's why I3 is going to be the same as I2. So now you look at it, I4 is kind of Q3 and Q4 are mirrored, like one current mirror again, right? So therefore, I4 is equal to I3 times WOL4 over WOL3. And you plug in the previous equation, you get iReference times WOL2 WL4 divided by WL1 WOL3. So it's fairly simple, just simply to ratio them up, and you will get the result. And I think we talked about this a little bit already in the previous lectures. I just try to find out the biasing voltage and the current in each branch. So in order to do that, we need to figure out where to start with, because there's so many transistors. A couple of steps is try to identify which one is current mirror or current source, which one is amplified. So often at times later on in the future, like you'll find some student come confused. I never get to understand which one is amplified, which one is a current mirror. So to do that, you can kind of start to look at where the input is, right? But in this circuit, it doesn't tell you where the input is. So therefore, we don't have a way to find which one is amplified to start with. But then we find, okay, well, let's look at which one the gate is connected to the collector. I mean, not gate, base. The base is connected to collector. If the base is connected to the collector, therefore it must be a current mirror. In that case, we'll find, oh, okay, that's easier. Because if you look at, oh, this is connected and they're back to back. This goes to be a current mirror. And so that's what we have. And then we have resistance over here. So this must determine how much current we have. But the problem is that we cannot get what we have because we can find the voltage over here, but we cannot find the voltage over here. If we cannot find the voltage here, we cannot get current, right? So that's the problem. And then we look at, oh, this one is base is connected. So this one must be the driving force or current mirror, and this ones all have the base connect with this. So therefore, this bunch of stuff is another current steering circuit. And then we look at this one here. Oh, this is connected. Okay, and this base is connect. So this one, everything here got to be a current steering circuit, another current steering circuit. And then apparently this is the reference one, and these are the results. And then look at the bottom here. Oh, this one is connected to the base. So therefore, this got to be like a current mirror type of device. And then this one is the result. And because this base is connected. So in fact, if you look at this circuit over here, it does not have any amplifier. Everything is a current source, a current steering circuit. So this number one step, we identified, okay, well, there's no amplifier, fine. So this purely is a current mirror device. A second step is, well, where do we start to calculate the voltage and current? Well, we need to start to look at where we can find the voltage. So you were given the bottom, you give 5 volts. Here you can give the ground, and the top you give 5 volts. But in the middle, you have a bunch of stuff. Like for example, from here to here, it's 0.7. So we can find that one. Because now again, we assume everything is in linear mode, right? So because this is connected, so we have here, we found here. And this bunch of stuff, we cannot find it because, you know, even though we know from here to here is 0.7, but we don't know here, right? So here, this is ground, and this got to be 0.7, so we found the voltage over here. But then we got to stop because we cannot do anything to the above. So let me write down so you guys know. Okay, so this is, oops. Let me keep. Let me slideshows start. Okay. So this one we found was 0.7. So from here to here is 0.7. I mean, sorry, from here to here is 0.7. But the base is connected to the collector, so therefore we have this one is going to be, because this is -5. So -5 plus 0.7, it gives you the voltage over here, which is -4.3. Okay, we got the voltage over here, so -4.3. And then we also got the voltage over here is 0.7. So I want to write this two down because I want to show you that the reason this is 0.7, this 4.3, because this is -5, but this is ground. So that's why the difference, right? We got that. And then from here, we said, we also got the voltage over here, which is the voltage drop over here is 0.7. So 10 minus 0.7 gives you here is 9.3 volts. So we got that voltage as well. And then we come to this side. I said here, from the top to here is 0.7 volts. So therefore we have here 0.7, but the top is 5 volts. So 5 is minus 0.7, we got voltage over here is 4.3 volts. Over here, connected 4.7 volts. So by doing this like 3 steps, we found, well, we got the voltage over here, and we got the voltage over here. And there's only one resistance in between. So therefore, we do this voltage minus this voltage, divide by this resistance, we got the current. We got current over here. So basically, it's 8.6, right? Divided by 20. So you got really something like 0.43 milliamps. Okay? We got this current. Now you got this current, all the transistors are matched. So you know how much current over here already. This is one single transistor. And you also know how much current in this one because there's 2 transistors. So you got this current over here. And this 5 kilo ohms times the current over here gives a voltage drop. So here you got the voltage over here. Okay. So you got the current over here. That's the first step. You got the current. And the current is the same. Let's call it I reference. Then this is I reference. This is 2 times I reference, right? And this voltage here is going to be 0 minus 2 times I reference times R4. You get this voltage over here. And then this I and this I reference, you see, the current over here is going to be I reference. And so the voltage here is going to be 0, like plus 10 times I reference. You got voltage over here. And you have current over here. So this current is the same I reference. And over here, voltage is 5 minus 8 times I reference. Okay, get that voltage. So pretty much by this time, we found all the voltages and all the current in the circuit. So this is example in the book. This is homework. So we had this answers mark it down for you, but I explained the steps from the beginning to the end. Okay. All right. So I think what we've done with chapter 8. Now we need to move on to chapter 9. So as I said earlier last week, chapter 8 is the most difficult one because it got so many equations, it got so many how to calculate. I don't know how to get. Let me go to the to the old way ahead. So chapter 9. Because they have so many equations and we need to get, one thing I think it's confusing is that sometimes we say, okay, well, sometimes you need to get to, like, you want to find out the output resistance, and sometimes you want to find the input resistance, and sometimes you say, well, we want a large output resistance. Sometimes you say, well, we need a smaller output resistance. What exactly were we doing, right? So that's all happened in chapter 8, because for current mirrors, for current source, we want the output resistance to be as large as possible. For current mirrors, current sources, current steering, just the current source, we want the output resistance to be big. But for our actual amplifier, like emitter follower or source follower, we want the output resistance as small as possible, because we want all the output to be working. Okay, and if your internal resistance too big, a lot of them is going to be wasted inside, right? So that's why we want that. So chapter 8, again, it's very difficult, but hopefully you guys, once we got through this chapter 8, you may be able to go back to appreciate, oh, wow, it is difficult, but I got the idea. I got why we want to do this, right? So then we're going to do chapter 9. Okay, so chapter 9 talks about differential and multi-stage. The two words already said what it is, differential. Why do we need a differential? So far, we have talked is everything like input is grounded, common source, common drain, common gate, and the input is grounded. The input has two terminals. One is connected to the amplifier, the other is grounded. And then the transistor is also grounded, either at the gate or at the base or at the source or at the drain. So it's one of them is grounded. But the problem is that in real life, a lot of times we cannot ground one terminal for the input. I'll give you an example. Like if you have this, okay, let's maybe go to a battery, like a battery pack in an electric vehicle. So each battery cell is 3.5, 3.6 volts, but your vehicle has like 350, 360 volts. So what they're doing is they put 100 battery cells in series. 100 of them in series. Now I want to measure voltage of a cell in the middle. What do? It's not a ground. If you measure the voltage of the last cell, yeah, that's a ground. Okay, I connect to amplifier. But if you want to measure the middle, you cannot do it because the other one is not ground. If you connect the transistor, like amplifier to here, and then this one, the transistor has the ground, but then this one is not ground, you immediately flow like a huge amount of current from the bus terminal to the ground, like hundreds of amps, you will burn everything right away. You cannot do that. So that's why we need to differential, which means we need to take the difference. So what we need to do, we take the voltage in the middle, that's the difference. So differential means difference between those two terminals. We don't care whether the bottom one is grounded or not. It can be grounded, but it doesn't have to be. So if we take the difference, we amplify it. So if we take the difference, we amplify, we call this a differential amplifier. And we cannot ground it, okay? Now, of course, you can ground it. Again, a differential amplifier can be used as a single-ended amplifier, but a single-ended amplifier cannot be used as a differential amplifier. So that's one. Okay, second word, multi-stage. Why do we need multi-stage? You already noticed that for the emitter follower, for the source follower, we have a gain almost close to 1. For the common source amplifier and common emitter amplifier, the gain is somewhere between like 20, 25, or maybe depending on the circuit, it can be 0 point something all the way to 50 maybe at the most. It's usually in tens, okay? So it's not big enough. Sometimes we want it much bigger. We want to be in the hundreds or thousands or sometimes even tens of thousands. How do you realize that? Well, we put it in a multi-stage. So you have one stage is 50 and you put another stage 50, what do you get? You amplify once 50 times, another time 50 times. 50 times 50, 2,500. Quite big, right? Okay, I'll put another stage. It becomes 125,000. So we put a 3 stage, right? So, oh, okay. And then you say, well, we want to increase the output resistance, but if we all use this common source, 3 stages together, we still have quite a big output resistance. Doesn't work. So what do? You add an emitter follower or a source follower, right? So now you get like 5 stages. Okay. And then sometimes say, okay, you got a differential output. It's in the middle of a battery string. We measure voltage, we got everything. But the output is also kind of a differential output. But in your microcontroller, you cannot take it. You say, oh, I need to have it's relative to ground. I need to know what it is. What do you do? Well, you need to convert this differential amplifier to a single-ended amplifier. You need another stage. So that's why you will see often 3, 4, 5 stages for amplifier. Increase gain, increase output resistance, and convert it into a single-ended. Okay, so you have multi-stage gain, and you have one stage of increase in output resistance, and you have one stage to convert it into single-ended. So minimum 4 stages. So that's what we do today. I mean, in this chapter. So we start by looking at this MOSFET, and we're also going to look at BJT. Again, once you understand MOSFET, BJT is simply the same thing. So I want to mention maybe before I forget one thing. So in this chapter, there's a huge section on large signal analysis. I'm not covering that. So I'm also not in the quizzes or in the final exam. So, but it's fairly simple. It's just analyzing the large signal like a DC operation, right? So it's if you go back to chapter 5 and 6, already covered. So it's here. It gives just a little bit more comprehensive view of that. So we're going to skip those 2 sections for both BJT and MOSFET. I don't remember the number. You can go into the book and find it. So we skip the large signal analysis and we'll focus on the small signal. So this is a differential amplifier. And some people look at it and say, oh, this truly looks like a current mirror. Does it? Does it look like a current mirror? Not really. Well, there are a couple of differences, right? In the current mirror, you usually put them in the same direction, but this is back to back, right? I'm sorry. In the current mirror, usually in the back to back. I mean, the base to base, back to back. But this is like not back to back, but head to head, right? Secondly, is that in the current mirror, you have the gate connected. But this, apparently the gates are not connected. They're connected to something else. They're not connected together. So this is not current mirror. So this is a differential amplifier. A differential amplifier would, by meaning, it will have 2 input terminals. So you would have a terminal input over here and an input over here. So you would have 2 terminals that you can take the differential. Now, we use this to illustrate how this works. In real life, you are able per se to have 2 volt input voltage, but you don't have to have like 2 separate voltage. You can connect them together to have 1 input. But this is to facilitate the analysis of the circuit. Okay. So by looking at the circuit, you see that there is a current source over here. But this again is built like from chapter 8, this current source. And then we have 2 transistors and they're matched. So for differential amplifiers, there's always matched, and then they are 100% matched. Except for like a design where, I mean, the manufacturing impurity process probably going to bring some difference. But otherwise, in theory, they are perfectly matched. So if they're perfectly matched, and there's current going through here, how much current do you think in each of this transistor? 50%. So they're going to be half each in this transistor. So they bias this transistor as half. And then what I want to do is to go ahead to draw the small signal equivalent circuit and see what they look like, so that you get a better understanding how this circuit is going to work. Okay, so let's see. So for Q1, from current. Okay, so for Q1, we have VG1 as an input. To the gate, and this thing has and this is connected. Okay, so this is R. This may be even RO, and this may be even RD. It's still going to be like this. So this is our VD1. Right? You guys see here. So I haven't drawn it here yet, but I want to draw this. This is your transistor over here. Okay, so maybe let me circle this one so you guys get a better understanding where the transistor is. So this is our transistor, and this is our drain, and this is our source. Okay, this is our transistor. So we got the Q1. Now we can draw Q2 in the same way, but the only thing that we flip it, we have output from the left side, right side. So we're going to draw that exactly the same, as a. So this is our transistor Q2. This is our G1, S1, G1 is our G2, G2, S2. Okay, so we got this circuit over here, and then this is our VD2, VD1. So basically, we got this 2 circuit equivalent circuit, draw this one and this one, and we also have the RD included in the equivalent circuit. So we have RD included here. We have RD also, this is RD included. RD here, RD here. This is RO2. The only thing we have not connected is this current source. And the current source is connected to source of both. But for small signal, we know that this is open circuit. And in the previous analysis, we always had a output resistance connected. But for this case, let's forget about it. Well, you say, can't you? Yeah, I mean, you don't have to. But if I wanted to, I could, because if I don't, I have a problem because, well, I don't have a problem. Depending on how you look at it, because I know the voltage over here. I know the current over here, so I can calculate the current of this one. the voltage across here. But the only problem is this current doesn't go anywhere. Because this is open, this current flowing, you can say, okay, if you neglect that, you say, oh, I just don't care. And then you might be able to actually, the answer is correct. The reason is this thing is going to flow somewhere. Because if you look at here, what happened? You see what happened? This actually are connected. So that's the key, which means, so what we are saying is that, well, yeah, so the current flowing here, it doesn't go this way, so it goes this way. And it will go this way and then come back, it will come back this way and up to here. And this is ground, so this ground is connected. So that forms a loop. So now we can add the current here. So the current becomes an open circuit. We get RO like of something of that transistor. Because these two are matched, and the voltage here and here, eventually it's going to be like symmetrical. So the current on this branch is exactly the same current as this branch. So there's no current here. So therefore, basically, yeah, I can connect it, but I can get rid of it because there's no current. If there's no current, which means this is ground. So this is the process how to get this. I remember I taught this class in the very first time. How can you get rid of this? I said, well, I didn't want to get rid of it. I just connect them. I have the current. But now you see, like this, no current here. So the voltage here is 0, which means we don't care. So by doing this, we should be able to kind of find VD1 and VD2. So we have VD1 equal to minus GM. Again, because they are all matched, so I'm going to just use GM instead of GM1, GM2, and R1, R2, right, times RO in parallel with RD. And we have VD2 is equal to GM times RO over in parallel with RD, and then times VG1 times VG2. And our VO is VD2 minus VD1 equal to minus GM. Actually becomes minus GM times RO or RD, and VG it becomes VG1, VG2 minus VG1. VG2 minus VG1. So this is our final output. If we want to get the gain, we will simply take A equal to VO over VG1 minus VG2, and then we'll get this gain to be positive GM times RO over RD. Okay, so this is how we get to the point. But in fact, I wanted to get into this early on because this makes your life really easy by looking simply the equivalent small signal equivalent circuit and doing the analysis step by step, and you find it. And later on, we're going to change these values, VG1 and VG2. We're going to change them and to see in different scenarios what happened. So that's how you're going to get to our next. Okay. So why I said we're not going to do the small signal, the large signal analysis, but still we want to be sure that you understand, the DC operation, the current and the voltage distributions, things like that. For example, in this case, how to calculate the voltage over here in DC, how to calculate voltage DC over here, and how to calculate this. There are a couple equations in this diagram that, if you recall, we did it in chapter 5, 6, 7, 8. Is that you have this ID equal to 1/2 times K W and times VOV squared, and then you have VOV equal to VGS minus VT, and you have to have VDS much larger than VOV to operate in saturation mode, right? So you got all these equations. And then we have, what else we have? Well, then if you know the current, you can calculate this VDD, right? VDD equal to VDD VD, not VDD, VD1, VD2. So VD1, VD2 equal to VDD minus 1/2 ID times RD. Now, the one important, very important thing when you do your quizzes the next one, you might find that if you don't plug in this 1/2, you're going to have trouble. Well, they use I, not ID, so maybe I should use the same thing to any confusion. So this current ID is 1/2 I. So each one has a 1/2 because this total is 1/2. It is I. But sometimes it's confusing because in the book, even some examples, they put a 2I here instead of I. And when you put a 2I here, so each one is I. So whatever it happens, you need to make sure that the current in the transistor is 1/2 of the reference current. So that's something you need to be careful. And then you, so in this figure, I think that's pretty much it. So now what we're doing is we're going to do this. So we're going to apply the same voltage at the base, at the gate of each transistor. If they are the same, so in electronics, we give it a name, but a common input or common mode. So these two are virtually the same thing. You can use the same voltage source, so that will be absolutely the same. Or you can use two separate voltage sources, but adjust them so that their voltages are exactly the same. So we call this common mode. So now we have this common mode applied to the gate. So regardless whether this is AC or DC, what do you think you will get at the output? What do you get? So we go to one slide before. We know that the output is VG2 minus VG1. If these two values are the same, what do you get? VO 0. So for common mode, you always get 0 output. So VO basically is 0 for VCM. So you have common mode input, you get output 0. Now you might question, okay, what's the point? You get common mode, you get 0. Well, later on you'll find that we do actually next week, we're going to discuss is that our input usually is the AC input that we want. But the AC input sometimes is so small that it cannot generate the needed biasing. If you have a voltage source over here, a negative voltage, which may be okay, you can have like from ground to here. But if sometimes if this is your ground and you have trouble to bring that to form your biasing circuit, so therefore we have a DC component on top of the AC. So that becomes a common mode input. So the DC is a common mode and AC is your small signal output. Okay. So for common mode, we're going to just talk a little bit. You know it, that's okay. We have this example 9.1. I want to go through this example to understand, because there's not much to talk about it in common mode. But then we want to get into the meats of this circuit to understand what are we talking about in a common mode? Why is this so important? Well, in this example, I don't even, let me see if I have the stuff written down here in the 9 point. I need to know what was given, what he wanted, so that then I can actually do the example. Okay, so it was given, VDD, VDS was given, K is given, VT is given, I is given, and ID is given 2.5. So, okay, yeah, so this was given, and this was given. So the first step, we want to find out if this current is 0.4, each transistor is going to conduct, half. So therefore, we have ID equal to half. If we know this, then we can calculate VD equal to VDD minus RD times ID, which 0.2 times 2.5 is 0.5, 1.5. So this gives you 1 volt. So we got VD to 1 volt. Now and then we from ID equal to 1/2 K WOL times VOV squared. From here we can get so ID 0.2 equal to 1/2 KWL is 4, then times VOV squared. So we get VOV equal to plus minus 0.1, I believe. What is 0.1? Let me see. 0.4, yeah, 4 milliamps. So that gives you two values, plus 0.32 and minus 0.3.2. And this VOV cannot be negative, so this is wrong, and this is correct. So we got that. So VOV is 3.2. And then this transistor matched, of course. And then we know that VGS equal to, or maybe we write the other way, is VO so VGS equal to VOV plus VT. So VT is 0.5, so we got 0.82 volts. So we got VGS. So where's VGS? VGS is from here to here. So we got 0.82 2 volts. And of course, match, so this will be 0.82 as well. Now we have here, the voltage of VS can be is basically what you're looking at is VG minus VS equal to 0.82. So therefore, VS equal to minus 0.82 volts. So we got all the voltages resolved for the whole circuit. So the next part is we're going to look at how we want to find the up limit and the lower limit. The reason is, well, okay. So basically, well, a little bit ahead of myself, because this one tells you, okay, if this is not 0, but this is 1, what happens? Well, basically, everything's the same because this is 0.82, current doesn't change, VGS doesn't change. The only thing changes is this voltage over here changes, right? So, and this voltage doesn't change. So I think what he wanted to tell you is that, you see, when the voltage increases over here, what happens here is the voltage over here increase. Just think about the extreme case. Like if this voltage becomes, let's say, 1 volt, if this voltage becomes 1 volt, which means this is going to be 1.82. Do you think this transistor is still working properly? If this is 1 and this is, let's say, 1.8, so this is still 0.82, which seems to be fine. Well, you're right. We look at here. This is 1 volt. So your VDS 1 minus 1, 0. VDS 0 is less than VGS minus, less than VOA. So this circuit doesn't work. So you can't go too high over here. If you go too high, the circuit will break its saturation region, so it doesn't work. So we can't do that. So that's why it shows you that when you increase this one, this will increase. When you decrease that, that decrease. But if you decrease this too much, what happens? If you decrease this too much, let's say this is minus 1.5. Let's say if this goes to minus 1.5, what happens? The voltage over here, VDS, well, this current source, that's right, but eventually it's a transistor. This is VDS. VDS becomes minus 1.5, minus 1.5 gives 0. The VDS 0 is less than VOA, so this doesn't work anymore. So you lose your current source. So therefore, you cannot go to too low, you cannot go to too high. So I think those next two questions was asking to calculate voltage over here, but this is easy. But what I want really to tell you is, I want to know how low I can go and how high I can go. That's the range. That's the common mode range. So this voltage has to be in a certain range. So what we're doing is when we find the range, we want to find, let's say, the upper limit. So the upper limit means like if this one or this one, it goes higher and higher and higher. It's so high that this VDS becomes a problem. So how high can we go? Okay, so we go to this one here. So this is so we use VD minus VS is VDS, right? So let's do that. So VD minus VS, so that's VDS, and it has to be larger than VOV, and VOV equal to VG minus VS, which is VGS, minus VT. So that's one step. So VOV is VGS minus VT. VGS is VG minus VS, right? So we got this equation here. In this equation, you will find that if I rewrite this one into one line, so I get VD minus VS equal to VG minus VS minus VO. So you have on both sides, you have VS, right? And both minus signs. So we get that VS canceled. And then we move VG on one side and everything else on the other side. We got VD plus VD plus VO. Okay, we have VG equal to VD plus VO. And what is VG? Well, VG is basically VCM. So VG is here, so VCM. So that's VCM, that's your upper limit. So in this example, we have VD is 1 and VO is VOV, sorry. VT is supposed to be VT, sorry. Yeah. Supposed to be VT, okay, VT. So VT is 1 and VT is 0.5. So we got to be 1.5 volts. Am I correct? A little bit. I want to make sure I got the correct answer. Yeah, it is correct. 1.5 volts. Okay. So I got to do 1.5 volts, which means VG can go as high as 1.5 volts for this circuit to be in saturation. But you see the power supply is also 1.5 volts. So this is a very interesting phenomenon. Means my input can go as high as the supply voltage. There's a name for that. In amplifier, like when you buy op-amps, sometimes they call it real to real. You'll find this terminology is real to real. Real means the supply voltage. Real to real means your input range is the same as the supply voltage. But here we have the real voltage is upper limit is the real. But we'll see the next step. The lower bound is actually not the real. But in the future, of course, you can design it such that it becomes real to real. Okay. So let's look at the lower. So the lower limit, we already said that this one will go out of saturation, which means this can no longer provide your constant current. And in the example, it says that you need a minimum of 0.4 volt, I believe. Let's see. Let's say yeah. So current source 0.4. So we call this VCS. So it has to be larger than 0.4 volts in order to maintain this current source. So therefore, now we look at our what is the VCM minimum. So which means we have to look at the voltage from here to here has to be larger than VCS. So which means we have VSS. Okay, so we have here is we call it VS. So VS minus VSS has larger than larger than VCS. Let's call VCS for now to make it easier later on to just simply plug in the numbers. Okay, so we and then VS and then we need to find out what VS is at this point. Well, VS is basically VGS equal to VG minus VS. So that's another equation we have. And then we know that this VGS, VG is basically VM. So VG is VCM. Okay, VG is here, VCM. So VG minus VS give you VGS. And then we have, let's see. VG, yeah. Okay. So then VGS has to be larger than VGS, no, actually no. VGS or VDS give me 1 second. Lower limit VCS VG minus VGS minus VSS VGS VG minus VGS. So VGS, yeah. So this has to be in saturation. So VGS equal to VOV sorry. VGS VOV equal to VGS minus VT. So VGS equal to VOV plus VT. Okay. So this is VGS over here. So we can plug in this equation to here, to here. So we have VG minus VS equal to VG minus VC equal to VOV plus VT. We got that. And then we have I'm writing myself. I don't know what I'm writing. So this is VG. Okay, that's what VG minus VGS. Oh, I'm sorry. Yeah, this right. My handwriting is terrible. So this is VG. VG minus, so VS minus VSS. Okay, so VSS. So now we have VS here. So we have VG here. So we have VG has equal to VS plus VOV plus VT. And our VS, we can plug in over here. So we got VG equal to VS is VS is equal VSS plus VCS, and then plus VOV plus VT. Okay, so finally I got the correct expression. So we got VG has to be larger than VSS plus VCS plus VOV plus VT. Now, this VSS, what I did was, you have to plug in a minus sign here. So which means this is going to be minus 1.5 instead of 1.5. Just if in the book, they might put a minus sign. So it depends on how you name it. So if you put a minus VSS, so VSS means a positive number. But if you put a VSS here, VS is minus 1.5. So regardless, this is minus 1.55. And then VS is 0.4. This is 0.2. And this is 0.5. So you put all these together, we got something like minus 0.28 volts. So we got this, come on here. We have this VCM mean to be minus 0.28 volts. And VCM max is plus 1.5 volts. That's your range. So in the future, when you do when you design a transistor, if you use this like this, you know that if your input range is exceeding this, you have to be careful because this is gonna make this transistors no longer in the saturation region. And then this process to get the VCM is very useful because if you want a large range, then this one thing you can do is increase the voltage range. Instead of 1.5, you increase that to 5 and -5, and your input range will eventually increase, right? Or you have to somehow to maybe reduce VTN, because if you reduce VT, your whole thing will start to decrease as well. So yeah, so that's some of the ways you can do for finding the common mode range. And next week, we're going to talk about the impact when you have a common mode, because I said many times that the transistors are 100% matched. But what happens in the process of making these devices, you cannot have them 100% matched. Then what happens? There's going to be some difference between these two outputs. So you're going to start to see, even though you have input the same, but because the N match all these two transistors, and you're going to have like output at the two terminals, right? Okay, so for common mode, we already saw that, and for differential input, which means we're going to have a different input. So instead of common mode, we have a different input. But in this case, we ground 2, and we have all the input at the gate at the gate 1. So in this case, if you remember the equation that we had, the output is, or the output is going to be like VD2 minus VD1 and equal to minus GM times RD in parallel with RO. That's what we get from last time. And we have VG1 VG1 minus VG2. VG1 minus, no, actually VG2 minus VG1, because we are using VD2 minus VD1, yeah. So it's going to be VG2 and VG1. So therefore, because VG2 is 0, then VG1 is VID. So we got this one into GM minus GM RO or RD in parallel with RO, then times minus VID equal to GM times RD in parallel with RO times VID. And we have the gain. We call the differential gain is VO over VID equal to GM. So here, apparently, we don't have to rewrite the equivalent circuit. We don't have to do anything. We simply use the equations that we applied before. So we get the output. And you notice a couple of things here. So why is that the gain is the same as a single-ended, like a single common source amplifier we had before? That's again the same, except that this is positive instead of negative. So this is one other way. If you want, like sometimes you have input, if you use the common source, the output is negative. You say, I don't want negative. What would you do? Well, you can use a differential amplifier and you apply the input at gate 1, and you take the output at drain of Q2, and you will get a positive output instead of negative output. Right? So that's something that you can consider. So this we get differential gain. If we apply everything at Q1 instead of Q2. What happens if we break this down? We apply half here and half here. which means instead of doing this, we're going to do this instead. But we do half here, we do half here. But you notice that this half is negative. Okay, this half is positive. So when you do the minus, because if this is positive, they become common mode where the output is 0. That's why you have to have positive here and negative here. So this is negative here. So this is negative. When you get the output, this is negative minus this positive. This will give you the same gain. You're going to get, like VO is going to be minus GM times RO in parallel with RD n times VG2 minus VG1. You plug in VG2 and VG1, you will find that this becomes GM, RO, RD, n times VID. And your A, again, is going to be GM times RO times RD in parallel. And then, yeah, that's it. So you get the gain basically the same as the previous slide. So if you split the input half and half, you got the same gain for the small signal input. Okay, that's split half to half. So this is all fairly easy to understand. And again, here, just using instead of drawing the small signal equivalent circuit, we basically simply draw the stuff on the transistor without the DC biasing. So this book uses quite a bit of that. So saying that, okay, I know that the transistor has to have DC biasing, but just forget about DC biasing. I treat this as like a small signal transistor. So there's no DC biasing. So we apply half voltage here, half voltage here. We have the source connected, and then we have half output here, and then half output here. We multiply this two. We got exactly GM/RD times VID. So this is your differential output. This is your differential input. And we're not going to draw too much. Okay. So then to facilitate future studies on this one, what they did was, instead of using the pi model, they started to get the T model. Because the beauty of the T model is that you got these two transistors converted into a resistance. I mean, to current source. That's the beauty part. But when you do this, you find, okay, you apply half here, you apply half here, and then you can calculate the current going this way. The current going this way is the same current over here, same current here, and you can find the voltage over here and the voltage here because all the current are the same. The only problem on this circuit is that you see this current is going up. Do you know why the current is going up? Huh? Yeah, because the negative VID. Because the negative VID, and suppose it's going down, but it's negative VID, we change the negative VID into VID, so the current going up. So that's manually we change it. So, and if you look at here, why this T model is more beautiful? Because you simply have this one loop. The current, it's just one loop. There's no branch, nothing. And the current over the whole circuit is exactly the same. Current flowing. And because the current flowing the same, you can easily calculate how much voltage is at the input side and how much output is at output side. So output divided by input, you got the gain. So that's why in the book it always says by observation. By looking at the input resistance, output resistance, we actually got like the gain. So in this example, like you got VD, for example, you got VD2 equal to GM times VID over 2 times RD. So you got VD2, and then you got VD1 equal to GM times VID over 2 times RD, but it's negative, right? And then you have VGS1, which is equal to 1/2 VID equal to there's a GM. Basically, yeah, so this is going to be like, well, this is just simply is 1 over Gm, which is resistance, times Gm times 1 over ID over 2. So you got that, I mean, which basically means that you got this cancel, you got exactly the same, 1/2 VID. And then you have this gain equal to A is equal to VD2 minus VD1 divided by VID. So you got Gm times RD. That's that simple, right? So doing this is that, this input, this output. So the ratio between these two resistance gives you the gain. So basically they are saying is the gain is equal to output side R over input side R. So this output side R total resistance and the input side resistance, you get the total gain. Now we can also add RO over here and then to ground, so you get RD in parallel with RO. So that's something we can do it later. Okay. So this is the same, and then half circuit. So the page we pretty much did most of it now. In this example, I think we still have time. Sorry, probably we're not going to take a break because it's too late. So let's just continue. I'll finish a little early, okay? So this example is actually the previous circuit with two minor changes. One change is that instead of open circuit to get output voltage, we got this resistor connected. So you think this is your load device. This is your load. And then at the source side, instead of purely ground, they connected two resistors over here. So now by this time, you probably understand that if you have a source resistance, the T model is the best one to do it. Okay, the pi model start to make a lot of problems. So remember how we did the T model in the previous slide? Let me see it here. So if I move this T model, right? So what's the difference between this one and the new one? We have two resistors here, and we have a resistance here. So we can easily add those two, and we can pretty much draw the small signal equivalent circuit. You're saying, okay, this is resistance here, and this resistor here, this resistor here, and then here we have current here, then we have current here, and we have resistor here. So this is RS, capital RS, capital RS. L, we have RD. So this is your equivalent circuit. Now you might say, well, it's still a little bit complicated because if we have RL in the middle, but in the book it tells you that, well, this RL we can separate into two resistance, and then we take the middle. Now I'll tell you why that is important. Because if you do that, you'll find that we're going to break this into two resistance. Now, this resistance is RL. You break them into two. Each of them is half. Right? So we have RL over 2. We have RL over 2. Now you have one current flowing from here all the way to here, all the way to here. And actually, this current becomes up, remember, and all the way here. These two circuits are symmetrical. And the input is also symmetrical, one half positive, one half negative, and the middle is the ground. And if you do the loop analysis, you'll find, well, this middle actually is 0. This middle is also 0. It's virtually ground. So that's why we call this a virtual ground. Because if you do loop analysis, you'll find that this voltage here is 0, and this voltage here is 0. It's in the middle. So if this is ground, this is ground. you see what happened to this circuit? We basically separate them into two. So basically what I mean, what I can do is I can draw, let me erase this one so I have more space. I can draw one half circuit. So basically this RD, these two becomes in parallel. This is ground. So I have this circuit, half circuit, and my output is right over here. See, by doing this, also using the previous slide, we can get the gain by doing the ratio between the voltage output and the voltage as input. Right? We can get the gain, and this is half input, so therefore the total gain is going to be like half. And then we get this side, it's another half. We add this two, we get 1. So we get the gain right away. We can have the gain to be the resistance of the output side, which is RD in parallel with and the input side resistance is 1 over GM plus RS. So just by the observation now, we can get it. You see, you might say, oh, wow, you by observation, you always said by observation. The book always said that. How easy is that? Well, we have to understand why we can do by observation because the current is the same. So the voltage drop here is equivalent to the input here, and the voltage drop here is equivalent to the voltage output. So that's why you can do that observation. So we got the gain. That's our half circuit. That's the example that we got. Okay, so this is how we got the gain. And so far, we had a current source at the bottom to bias the MOSFET. So the function of this one is to bias. And on the previous example, you said we had this low over here. And that's a resistance. But in fact, in our ICs, we rarely use resistance as a load. What do we use? We use current source as a load. So the top, you can see the top, why their current source is not amplified? Because first of all, the gate is connected. And secondly, the input of Q3 is a DC voltage, it's no signal. So for AC, that's grounded. So the top two is a current source. So when you have a current source as a load, do you remember what we have eventually? I mean, this, basically, we can draw the equivalent circuit like this. This is the current source, and this is for the biasing, okay? But the top one is a current source with its output resistance, and then this one, and this one too, with the current source with output resistance. But a current source for AC is an open circuit. So basically, we get rid of this, we get rid of this. Then we have this, basically the same. We basically have the same amplifier, but with two resistance. And this two resistance is the same as RD that you had on the previous slide. But instead, this is RO3, this is RO4. This resistance, even though they are also in the kilo ohms, tens of kilo ohms, but they are the internal resistance of a transistor. And a transistor is very small. We're talking about nanometers. But if you actually have a RD, that's going to be micrometers or even millimeters. Okay, that's why we like current source as a load instead of a resistance. Okay, so by this time, I think you already got the idea is that for differential amplifiers, again, half circuit, probably. And if you have a BJT, you would do the same thing. The only difference, of course, the input resistance now is R pi instead of infinity, and this current source here is the same thing. So there's RC at the top, everything is the same, except if we draw the pi model. If we draw the pi model, it becomes this. So you can see that, yeah, so this is a ground. You can see that these are the two transistors, and this is your Q1, and this is your Q2. You got only the difference. The previous one, you don't have any resistance at the gate, but this one you have resistance at the base. And this one you have resistance at the base. Same thing. But then you have the emitter connected. So we can have the emitter connected. Now you can, this one here. Now for AC, you might say, okay, well, this RO of the current source, yes, that RO, but current flows from here to here, and this becomes like really no current here. So basically you can get rid of this one. I mean, no problem. And you take your output over here, and the gain is exactly the same. There's not much to talk about here. The BJT pair, again, analysis. So the only difference is that we're gonna like the DC biasing is different, but for the AC analysis, so the one difference is the DC biasing. Another difference is the R pi instead of infinity input resistance. Okay, so I think I'm going to do this example, and then we can conclude the class. So in this example, this is more like this is a PMOS. I mean, P-type BJT. So instead of, so if you look at this, you already notice that this is a differential pair. But what they did is they apply input at Q1, but they ground Q2. It's like a Q2 is now have a small input, which is ground, 0, but Q1 has an input. But the problem is that if the difference are so big, these transistors may actually run out of linear mode. So we can look at it. So let's start, when we start to talk about it, we say, what is, okay. So we have to start by assuming like one of them is in linear mode. And then we can look at whether it's a correct assumption. So let's assume Q1 is in active mode. So if Q1 is in active mode, your input is 0.5 here. So what is the voltage at the emitter? This is PMOS. 1.2, right? So 0.5 plus 0.7 is 1.2. So if this is 1.2, you see this is the ground, which means this got to be in active mode. Like if it is in active mode, the maximum you can get is 0.7. So therefore, you cannot have 1.2 here. So this goes back actually to 0.7. Okay. Now, okay, say, okay, if this is 0.7, this one is in active mode or linear mode. Now, if this is 0.7, this is 0.5, what happened to this transistor? See, from here is 0.7, there's 0.5, which means the difference between these two is only 0.2 volt, which means this thing is in the, well, yeah, you're right. It could be in the saturation mode because apparently it's not in cutoff because there's a difference. So if it's not in cutoff, this is 0.7, 0.5, which means the voltage drop over here must be too small. So therefore, this goes to saturation. So this basically just tells you that if this two input difference is too big, you got a problem for BJT. Okay. Now we can then calculate what we have for like each current. Like if this is 0.7, then we can calculate current over here. But we cannot get the current of this two.
Why? Because they're not symmetrical, because this one in active, this in saturation, therefore we cannot get the same current, we cannot split evenly. But if this is in saturation means we can get this 0.2, so this 0.7 minus 0.2, we get 0.5, so we get current on this one. We get current on this one, total current minus the current of this one, we get the current of this one. So that we can do. Now, the other way that you can do is to do this IC equal to IS times e to the VB over VT, so that you can get a current as well. So basically, yeah, so that's, you got the example, and then this analysis. Okay, now we get to the T model, which again is very simple, because when you get to the T model of the BJT, it eliminates the R pi. There's no longer R pi. The only thing you got to care for is this IB over here. But for MOSFET, there's no current. Basically, the current here are the same. But here, since there's IB, the current over here is not exactly the same as the current over here. Okay, but if you neglect this current, actually you won't be too much wrong, because the difference will be 1%. Okay, but if you take that into account, you will have your like equations like this, and then we can get basically the gain. Like in this case, if you neglect IB, and your gain will be like no here, and therefore your gain will become something like the same. Your gain will be almost the same, like alpha times IE times RC, or at the top, this one here, you get the top resistance, and divide by the bottom resistance is IE times RE that you got here, and this RE cancel, you got, that's your gain. Okay, so it's fairly simple to get the gain, like it's analyzing, but you can also do like a half circuit and equivalent half circuit, and then it's like this. So what I do is I'm going to stop here, and next week we're going to start with example 3, just to enhance what we talk about, and also because of the BJT, right? And in addition to have the gate input, but now it has an input at the gate, at the base, and it also has a resistance at the emitter. So it makes it a little bit more difficult. But we'll do this example to show you that it's actually fairly simple to get the gain. Okay. Okay. Well, yeah, we finished a little early, so good luck. We'll see you next week. And next week, our quiz is going to cover the 2 current mirrors we talked about earlier today. So probably 1 question each. And then we'll talk about differential amplified. You're probably going to see common mode and differential mode. Look at the gain, things like that. I would say just focus on MOSFETs, and BJT we're going to review next week. So it's going to enhance your learning. So just give you a like heads up on what's going to happen in the quiz. Okay. Good night. Yeah. We can schedule office hours for Tuesday. Tuesday. Let me see my schedule. I'm pretty sure you can. Yeah, you can. Yeah, just it's around the same time, right? Like that's fine. That's fine. Yeah.